Still getting ready here. Just a minute. Oh, look at that. Somebody else taught mechanics. Okay, so let's see. No extension cord, but one outlet not so far away. We'll make do with that. So, anybody got any idea what this concoction might do? I should have brought this a while ago, really. Remember when we talked about the Van de Graaff accelerators or separate. Well, it's got the brush on the bottom and the belt that can rotate, and it's basically moving charge to the top, right? And so it's a device that's going to let us just separate charges without me having to rub the silk cloth on the glass myself or something like that, right? And so what are we going to what's going to happen when I turn this on here in a moment? What do you think will happen? Any ideas what will happen? So we accumulate more charge, right? So we are going to accumulate more charge on here. Then what's going to happen eventually? We'll have a large spark, right? So you want to receive any text messages or so, do that before I turn this on, because that's going to mess with your cell phone. So all right, I just want to make sure to keep my head further away than this thing, otherwise you will hear a bell. Oh, that belt is a bit weak. That belt is wobbly. I don't know how well it works today. You could see a small spark. That wasn't too spectacular. Somebody wants to turn off the light. We can see the spark from the back too. That was a bit louder. Took just a while. It's going to come together here. So right now what's happening is the electricity flows back through this black cable here to the ground that I've connected to the box. Of course, what's more fun is when I hold this and we form a chain, everybody holding ends, and then the last person touches that negative terminal. You get a little jolt going all the way through. Not dangerous, but so why is it not dangerous? What did we learn about the dielectric breakdown of air? That was something like a megavolt per meter, right? Well, this is less than a meter, but it's close to 10 centimeters, right? So a megavolt per meter, 10 centimeters, that means I still have 100 kilovolts here. 1,000 times the voltage that you get on the outlet. If you stick your fingers into the outlet, that's really harmful. So how come I can have 100 kilovolts right here and nobody dies? Because there isn't enough power behind it, right? The amount of charge that's on there, it can sustain a current for a short moment, but then the voltage drops very quickly as the spark develops, right? All right, so, okay, so that's fun. We can see sparks flying. Any credit cards that need erasing, I can hold them in between again. No, all right. Well, okay, let's do something else. If I turn this on and I bought a couple of aluminum dishes, what do you think is going to happen when I turn it on again? This is called Sense the UFOs flying. Sometimes they all slide off at the same time, but if it works nicely, it works really nicely. Ah, well, all right, kind of. Oh, and there it goes. The belt slipped off. We almost got it. I've got to fix this at the bottom, and I don't know that I have the time to do it now. So anyways, this is really what I should have shown way back when we talked about static electricity, but I didn't have it available. Then somebody else had checked it out of the demo room. So that's electrostatics, right? And we just see like charges repel, right? That's what made it take off, right? And so on. And we did see dielectric breakdown in air, and that eventually, when the charge builds up enough, we can jump a fairly large gap, right? So really, the demos that I wanted to do today, they are not on electrostatics, but on magnetism. And so I think for that, we can turn on the other light again as well. So for magnetism, let me cover a little bit of the presentation before I do that. So we know Lenz's law, and we know some of the concepts behind what I'm going to show in a minute. So again, we've talked about magnetism, but we haven't really talked about Faraday's law and that aspect of magnetism, magnetic induction. And so as the projector is coming up, give me one moment here. Where are my slides? All right. Okay, so we've gone over the overview and we have talked about some of the initial experiments, and we've talked about motional EMF. So again, the idea is if I move with an external force pulling until I reach the speed, the bar sideways, then there's a force on the charges in that bar, and that's V cross B, so an upward directed force that's pushing the positive charges upward until I have essentially a charged capacitor, right? Positive forces, charges accumulating on top, a lack of positive charges, negative charges on the bottom. And so there's an electric field that establishes itself until the magnetic and electric forces that act in opposite directions exactly balance out. And then I have a potential across the two sides of the strip. And that potential difference is, of course, the electric field times the length, right? That's a potential difference. And since the electric field has to be in magnitude such that the electric force QE and the magnetic force QVB cancel out, I get a potential difference, a motional EMF of magnitude VLB. And so the metal piece moving in a magnetic field acts just like a battery in that there's an electromotive force across the sides of that strip. Okay, so of course the orientation matters. In this case, if I move my metal piece as shown in this figure, what distribution of charges am I going to get in this case? Nothing, right? There's zero angle between the direction of V and B, and so the cross product is zero, and so I get no induced charge separation in this case. How about this configuration? Now I have V and B perpendicular, and so I get charge separation such that positive charges move to the left, as I had indicated, right? And then I would get a potential induced, I would get a motional EMF between the two sides of this strip, right? Okay, well, is this really practical? Can we, observe this? Can we see this? Let's see how we can get to maybe something we can observe. So let's say I'm pulling this maybe steel or aluminum bar indicated in gray, and I'm sliding it so that it's an electrical contact with copper rail or whatever this color is. And so as I'm moving it, there's again that motional EMF that's coming about. And since there's a closed loop circuit, a current can flow around that external path that this EMF is applied to. And so I get a current that by Ohm's law is just given by the voltage, the EMF divided by resistance. And the EMF is, as we saw on the previous page, VLB. And so we get a current flowing here, right? Okay. Now, wait, a current is flowing, but we have a magnetic field. So what happens with that current flowing and the magnetic field? Moving charges in a magnetic field, there's a force on them, right? So what's the force on these charges moving up here? IL cross B or QV cross B, right? So the direction of the current cross the magnetic field gives me a force to the left, right? So I'm pulling it, to the right. Me pulling causes a current. The current in turn produces a force to the left. Okay. That's Lenz's law, or one way of thinking about Lenz's law. It counters the external effect that's causing it, right? So I'm pulling, that's causing a current. The current causes another force on all these charges and hence collectively on the bar that moves the other way. So another way to think about it is, well, if there is a current, that current is going to heat up the resistance, right, that it's flowing through. And so if I do this for a long time, then this metal rail and the bar are going to heat up by resistive heating, right? So there's electric power associated with the current, IR squared, or V squared over R, right? And so that energy, that electric energy that goes into heating has to come from somewhere. And so where does it come from? You may say if it's moving at constant velocity, then I can stop pulling, right? Zero net force, it will keep moving. Yes, but zero net force, not zero applied force, because we just saw there's a magnetic force to the left if it's moving to the right. And so to keep it moving, I have to keep pulling. I have to keep doing mechanical work. And that's what's providing the energy that goes into heating the resistance. And so the power provided by pulling, the again, work is force times distance, right? Work per unit time is power, and so distance per time is velocity, right? So power is mechanical, power is force times velocity. So as I'm pulling over, that input power has to equal the output power. And the output power is the magnetic force times the velocity. But the magnetic force, as we've seen on the previous page, that's ILB, right? Cross product gives me just 1 for the sign. ILB, and the current, because I was pulling, was and the EMF was VLB, and then the current was EMF over R, and so put it all together, I get V squared V squared over R, multiply by another V to get the power done by transmitted by that magnetic force, and I get this expression. So all this power is dissipated by the resistance of the circuit, ending up as heat, and that's what I need to do to pull. Okay, so I need to provide this power that gets dissipated as mechanical work. All right, so we've said that if I pull, there's a magnetic force to the left. So it seems then maybe if I can push instead, it will be easier, right? Because then I'm aligning with the magnetic force. So let's think that through. What happens if I push? It doesn't become easier, right? Because the magnetic force is changing direction too. So I'm now pushing or pulling from the other side, however you want to look at it. Okay, right hand rule still. Velocity in the direction I'm pulling, right? Or the external agent is moving this, right? So if it's moving this way and the field is into the page, the cross product points downward and we get positive charges down here. Whereas on the previous slide, we got the positive charges up here, right? So we are reversing the polarity of our battery, of our EMF. And the current's going to flow the other way around, right? And so now we have a current flowing downward. We still have the magnetic field into the page. And so we have a magnetic force on the charges moving and hence collectively on the bar that they are flowing in. That's now pointing to the right. So no matter which way I pull or push, the magnetic force is pointing in the opposite direction. So it's all the right-hand rule. And let me do it one more time. So velocity to the left, field into the page, effect downward, right? That was the first one to figure out the direction of the current. Okay, now the second time we are doing it, we still have the field into the page, but now it's the moving charges. The charges are moving downward, so I turn 90 degrees, and this is the force, right? And so you see how just doing the right-hand rule twice, I get pulling this way causes a force that way after I do it twice, right? So that's twice the right-hand rule gives me the opposes what's causing the current, right? What's causing the current is me pulling this way, so the magnetic force ends up being the opposite way. And so you can always figure it out with the right-hand rule from first principles, but you can also remember the conclusion of that exercise is always going to be that the magnetic force that comes about counters the cause of the current that produces the force, right? So Lenz's law, opposing the effect that's causing it. So, by the way, this is not what a real generator looks like, but this is a device that converts mechanical energy into electrical energy, right? So in a sense, this is a very simple generator, right? All right, so let's see if we can figure this out one more time. Suppose I'm moving the metal bar to the right, and I'm observing a current induced clockwise as shown. What's the direction of the magnetic field that's not shown here? So we want all of them to be perpendicular to one another, right? If any two of them are parallel, then we don't get a cross product, right? And so we have current and velocity. So we need a field that's either into the page or out of the page, right? Because the directions up and down and left and right are already taken. So into the screen or out of the screen. And so, all right, so what's what? The velocity is in the magnetic field causing the force that's moving the charges, right? So the third finger, the middle finger is pointing up. And the first one is the velocity. V cross B is the force, right? Q times B cross B. So into the page is the direction of my index finger, right? Magnetic field is the index finger, right? All right. I saw several of you answer that correctly, but I saw some of you also, you know, just maybe it was just this problem or however. So anyway, into the page is the right answer here. All right. What happens if instead of a loop, I just have a sheet of metal? Well, if I move the metal sheet, there's going to be eddy currents. I still have a region in the magnetic field and kind of like the outer rail, right? And so there are loops of different sizes, but I get basically a pattern of eddy currents, kind of like two whirlpools of currents. And those currents, again, produce a force that counters the direction I'm pulling in. Okay. So let's see, is that just hypothetical or is that real and can we observe this? So it's actually this retarding force due to the eddy currents is a form of magnetic braking, right? So it should be observable. We should be able to slow down, for example, a pendulum. And so if I take, you know, an aluminum plate, it just makes a very simple, nice pendulum. And so then I can take a magnet, and so if I, unfortunately it twists sideways, but hold on here. Did you see how it's torqued? Okay. It's not because it's hitting it, right? It swings. Oops, where now it was hitting. But you see how it just stops. All right. There's no trick. It's the magnetic field. It's eddy braking. How can we prevent eddy braking? Suppose we have a setup where we don't want that to happen. I have maybe less material now, but I have these cutouts, and so I can't have large currents going around, right? The circuit is broken there, right? So I'm still going to end up with tiny eddy currents, but only within each of these prongs, right? And so this one swings just like the other one, and in the magnetic field, it doesn't slow down, right? Sorry, it's twisting a bit. I didn't find the correct mount for this, but you can see the idea, right? So it's touching the poles, that's why you hear some noise, but you see this one didn't like stop like it hit a wall, right? So you can try this yourself when we take a break later on and see it up close and do it yourself if you like. But so magnetic braking and eddy currents are real and we can visualize it this way, right? All right. So Well, all right. We already talked about flux before, but let's review. So we talked about electric flux when we talked about Gauss's law. The electric flux through a closed surface was proportional to the enclosed charge enclosed in that closed surface, in the volume enclosed by that surface. Now we want to talk about magnetic flux through an area, not necessarily a closed surface. And so if we have a rectangular wire loop with an area A times B, the two sides, and put it in front of a fan, then again the volume of air crossing through it is going to depend on the orientation, right? I can blow air at it at the right orientation, or I can blow it above and below and none of it goes through, right? So it's the area times the cosine of that orientation angle that's giving me an effective area. So the effective area is shown here in this reddish color, whereas the bluish color is the actual area, and the effective area is smaller than the actual area by the cosine of this angle. And so if I have the orientation just right, I get the largest flux, the largest effective area is the same as the physical area. If I tilt it, then the height of this that I see looking on sideways is just b times cosine of that angle. And if I tilt it by 90 degrees, then I really don't see any area. I just see a line. None of it goes through, right? And so we already had defined the area normal vector, and then the area vector that encodes both the orientation of this area in space, as well as the magnitude in square meters or square inches or whatever, right? It doesn't have any information if this is a round loop or a square piece or whatever. That's not part of that information, but it's a useful definition. And then with that definition of the area vector, we can define magnetic flux denoted by the same symbol we've used for electric flux, only with a subscript m instead of a subscript e. So capital Phi sub m is for a flat surface the effective area times the magnetic field, or area times magnetic field times the cosine of that angle. And so magnetic flux naturally has units of magnetic field times area, Tesla meters squared in SI units. And when we talked about electric flux, we really didn't give that combination of units of electric field times unit of area any other name. We just talked about volts per meter times meter squared, right? We didn't have a different name for that. But magnetic flux and magnetic induction is so important that here we actually do give it a different name for a physicist who did some of this work, Weber. And since capital W is already used for watts, we use WB for the unit of magnetic flux. Okay, all right. So then we can calculate magnetic flux and, well, all right, which loop has a larger magnetic flux through it? If in one case we have a field that's twice as strong, and in one case we have a square that's twice as wide. right? You can kind of just count the dots that go through, right? Okay, so twice the field would make it twice as much if everything else is taken the same. But twice the width means for a square also twice the height, and so it's 4 times the area, and times half the field still gives me twice the flux, right? So we have about 4 field lines for this small square, and we have more than 4 over here, right? So it's loop B that has a larger flux through it. Okay, suppose a metal loop is being pulled through a uniform magnetic field. Is the magnetic flux through the loop changing? Any moment in time, we are just having the same number of field lines, right? It's not changing as we are pulling, as there are some field lines not any longer in the area of the loop. New field lines come in, and so it's the same flux at every time, right? But what about when we are rotating the loop in a uniform magnetic field? Now we have that cosine effect, right? So that's going to change things. All right. We've so far considered uniform magnetic fields and flat surfaces, but of course, if we have an area where the magnetic field is increasing, then in general, we need to just integrate B dA over the area of the loop, right? So this again is really very similar to what we've done with the electric flux already, right? Why would we have a change in magnetic field? Well, we've seen that it's changes in the position of a magnet, for example, that cause an induced electric field, right? And so, as we've seen both with the moving bars, as well as now are about to see with induced currents in loops, Lenz's law tells us that there is, when we move the magnet, an induced current in a closed conducting loop if and only if the magnetic flux through the loop is changing and the direction of the induced current is such that the induced magnetic field opposes the change in the flux. All right, so if the needle here moves because I'm pushing the bar magnet inward, then which direction does the magnetic force act on the bar magnet? Countering that. So the force would be upward, right? So it's like replacing the loop with a tiny magnet that has its north pole above and south pole below, right? Because north and north repel, right? And so which way would the current move to get a north pole above and the south pole below? Right-hand rule, I wanted to go to the right in front and to the left behind. You see that? So it's going to move, well, from a top view, it would be counterclockwise, right? Makes sense. So that's how we can apply Lenz's law to figure out the direction. Okay, so it's opposing the direction that's causing it. So again, pushing the bar magnet into the loop causes the magnetic flux to increase in the downward direction. To oppose the change in flux, which is what Lenz's law requires, the loop itself needs to generate an upward pointing magnetic field, right? That's what it is. With the north, basically causing the north and the south pole induced, right? So the induced current ceases as soon as the magnet stops moving, right? We only have that effect while there is a change, while there is motion. Okay, now be careful in this case, as we are pushing down and get closer, the magnetic flux increases and it's pointing downward, right? And so the arrows of the induced field point in the opposite direction to the B field of the magnet. But that's not always the case. What if I'm pulling the magnet upward, but the North Pole still is at the bottom? Well, I'm still having magnetic field lines going through downward, right, out of the North Pole back into the South Pole. But I'm pulling up, so what's the change? It was strong pointing downward at first, and then it was less strong a little later when I moved the magnet upward. So although it's pointing down early and still pointing down later, the change is upward, right? And so as I'm pulling upward and the flux decreases, I'm getting an induced field that tries to counter that decreasing flux and hence points in the same direction as the field, right? So it doesn't necessarily oppose the direction of the field, it opposes the direction of the change in the field. Okay, so the induced field points downward, which would correspond to basically having a south pole above and the north pole below. And so a south pole would attract the north pole, right? And so if I'm pulling out, the induced current pulls me back in, right? Or counters the change, right? In every case, counters the change. Okay, all right. So if I move a bar magnet from below towards the center of the wire loop, which of the statements is true? There's a clockwise induced current, counterclockwise induced current, or no induced current. So if you aren't showing me an answer, as are you lost or are you? It's how. Let's see. So I'm moving the bar magnet up. So I'm going to want magnetic force induced that pushes it down, right? How would I get a force that's pushing it down? I would want to have a north pole below and a south pole above, right? Because the like poles repel, right? So I want to get a field that's pointing downward inside the loop and then up outside the loop, right? Or down in the loop, up behind the screen, and so on, right? Down, up, down. So how do I get that? Down in the loop. If I'm in front, I want to curl my fingers this way. And so for this wire, I want to go left. And then when I'm behind, I want to go down in front of the wire. And so in the back part, the current needs to flow to the right, right? So then as we are looking from the top, we would get a clockwise current producing the effect opposing the change, right? So, or again, we can, I think thinking about it in terms of the forces is maybe the most direct and most intuitive to me, but we can also think about it in terms of the flux, which is really where Faraday's law is getting us. So if I move up, the upward pointing flux is increasing, and I counter that by having a field pointing downward in the loop, and that's giving the same result, right? So a downward field in the loop is looking clockwise from above. I guess maybe some of the confusion is that clockwise and counterclockwise only makes sense if you specify if you look from above or below, right? So usually we assume we are looking down from above unless otherwise stated. All right. How about this situation? The bar magnet is pushed towards the center of the Bayer loop, which is true. In this situation, do we get any change in flux? So this time we may get a change in the number of field lines, but any field line is either going to cross through to the top and back down, or not crossing through the loop at all, right? So due to the symmetry, there is zero flux in this case. And although the magnet moves, the number of plus through the loop and minus through the loop flux lines remains the same, right? All right, so this is a kind of long-winded way of summarizing just every time the same general principle. So, all right, if B is pointing up and it's steady, we have an upward pointing flux, but we have no change in that flux. No change in flux means no induced field and no induced current, right? Okay. Up and steady, no change, no induction. Up and increasing, so either by moving the north pole in from below or moving the south pole away from above, well, it's pointing up and it's increasing. So that's an increase. There is a change in flux, and that change is pointing upward, up and increasing. So countering that, we have a induced field that's pointing downward, and that's due to a current, well, downward, and the front wire, it's to the left in front, to the right in the back. So induced current is clockwise. All right, so up and increasing gives me a clockwise current. Up and decreasing, so it's still pointing up, but I'm pulling my north pole downward away. So it's still pointing up, but it's lower later on. That means the change is negative, right? Large pointing up early, still pointing up, but not as strong later. Change is downward. Induced field must be upward. What's producing the upward induced field? It's a counterclockwise current, right? You can, again, either do it with Lenz's law like this, or you can do the right-hand rule twice, right? All right, and well, if instead of up, it's pointing down, just mentally turn the past 3 slides on its head. Down and steady, well, it's still no change, steady, no change, no induced field, no induced current. Down and increasing, so now I'm approaching with the North Pole from above, or however I'm doing it. Where the change is then downward, induced field has to counter that and point upward. How do I get an upward field? Upward in the middle of the loop is to the right in front, counterclockwise. Right. All right. And down but decreasing means it changes upwards and the induced field has to point downward, and induced field downward, as we've already seen, means a clockwise current, right? All right. But all these 6 different cases, again, I wouldn't try to just mindlessly memorize this as like a table of possibilities. The principle behind it is Lenz's law, and the point of these slides is to just over and over confirm for yourselves that you can apply it correctly, right? All right. So the strategy we are using, or tactics for applying Lenz's law, we need to determine the direction of the applied magnetic field, find where is the North Pole or the South Pole, or which way does the current go through my coil, and so on. Find the direction of the applied field, determine how that flux is changing. Did we close the switch and the field is increasing? Did we open the switch and the field is decreasing because the current is decreasing? Or, you know, are we moving the magnet closer, further away? Then determine the direction of an induced field that will oppose what we determined as a change in step 2. And then determine the direction of the induced current if there is a change that needs to be countered. All right. So suppose we have a current in a straight wire, and this current is decreasing over time. Then what's going to happen with this loop? Are we going to have a current go around that loop or no? And if there is, which way is it going? So early on, we have magnetic fields through the area enclosed by the loop. That's pointing into the page by the right-hand rule. And later on, we have a field that still points into the page by the right-hand rule, but as the current is decreasing, the field is decreasing. And so we have a change that's pointing out of the page, right? And I counter a change out of the page by having an induced field pointing into the page. And I'm getting a field pointing into the page by having a current in this loop going clockwise, right? Into the page in the loop is up here, to the right on top, to the bottom on the right side, and to the left on the bottom, right? All right, so again, that 3-step process. The change is out of the page, so we want an induced field into the page as indicated with these X's, and that's caused by a clockwise current. All right, we are pulling the loop out of the magnetic field region, which is true. So field pointing into the page, but less flux later as we are having fewer field lines point through. So change out of the page. So induced field into the page. So same as the previous loop. Also got to be clockwise, right? All right. Immediately after the switch is closed, the lower loop exerts what on the upper loop? So we have a battery here with plus and minus, right? We close the loops, there's going to be a current. What's going to be the effect? We are going to create a magnetic field. So where there were no magnetic field lines early on, there are going to be some later on. And so I'm going to want to counter this with field lines that point the opposite way. And so I don't even have to trace if the positive side is such that the current here is clockwise or counterclockwise, because in each case I would want to counter the effect. And so if this creates a little north-south pole, this would create a little south-north so that the two north poles repel. And if this happens to be connected the other way around, then there would be two south poles that repel, right? In either case, there's no flux through this, and so later on it still wants no flux through it, right? Opposing the change, and that happens when it just moves away, right? So it's going to, one way or the other, have an upward force acting on it. Now, since this is the positive side, we can tell the orientation of the current. And so with that direction of the current, we are getting a little north here and the south there. But that's repelled with an induced field that's countering that change. So it's the field is due to this lower loop is pointing upward and increasing. So to change that, the induced current points downward. And that's when we have a clockwise current in the upper loop. So the induced field points downward. And then the effect is an upward force between the two loops. Okay? Is that real, or is that just a nice little thing that we can't really verify? Well, let's see. I have here a coil. You see this reddish color wire. It's not just one turn, but many, many turns. So it plugs into the wall, but it's just a little device that sends a direct current through the coil when I push the lever. And then we can see what happens. So for my upper coil, I brought different possibilities. So there's just a little aluminum cylinder, hollow aluminum cylinder, right? Like the upper turn of my coil, and that's the lower turn. And I can let it, slide over it, but similar in concept, right? You see, that's what it is. So let's do this. So plugged in and ready. And now if I activate it, whoop, I hit the ceiling. All right. So that's how physicists shoot things. No explosions, no chemical reactions, but magnetic propulsion. Okay. I have a few other choices. I can do this with a smaller aluminum ring. And well, there's less weight, but there's also less, less material to have a current induced in. And so it's similar. It actually doesn't work as well as the larger one, right? So instead of aluminum, I can use copper, which is significantly more heavy than the aluminum. And so it's going to have the same current induced in the ring, same Faraday's law, same Lenz's law. But because it's heavier, it's going to not launch as high, but it still launches, right? All right. Well, isn't this all just some magic trick, and this plastic ring here really pushes it upward? Well, let's try another ring, and I don't know if you can see this. This is kind of like my other aluminum cylinder, but it's got a little slit in it. Okay, so it's essentially the same weight, the same material. However, if I cut the loop, I can't have a current flowing around. And so what's going to happen with this one? Not going to launch, right? You hear when I push it, right? It's humming, and it's not launching because it's cut, right? So, all right, but we can definitely magnetically launch, so there is an upward force, and it's going to have an effect. With single turn coils, not too much, but once we get many turns, we get many times the effect, and we can have some fun. All right, so we haven't talked about the magnitude yet, so let's finally do that. The electromotive force is induced in a conducting loop if the magnetic flux through the loop changes, and the magnitude of the EMF is d Phi by dt. So the change in magnetic flux with respect to time is the induced voltage. So we can just write, magnitude and then figure out the direction by Lenz's law. Or we can also write the induced EMF as minus d Phi magnetic by dt, where we use the fact that there is an orientation to an area, right? So if I have this area A and I can randomly choose, it's not a closed area. So when we had Gauss's law, we said outward is the direction of our normal vector, right? Now I don't have an area and now I don't have a volume enclosed. So really I kind of have to select, but let me say upward is the normal direction. And let me now say I'm bringing North Pole closer, okay? Then with this convention, I have field lines crossing through, and so I have B pointing upward, and so I have my magnetic flux as I've drawn it, integral over the area of B dot N times dA, right? I could write dA with the arrow, but let me just write it, writing dA as the normal vector direction and magnitude separately. And so with this convention of N, this is a positive quantity, right? these vectors are basically, aligned more than, the angle between them anywhere is less than 90 degrees, right? So I'm getting positive contributions that I'm adding up. And so it's larger than 0, and it is also increasing, right? I'm bringing the magnet close. And so that means the change is larger than 0, right? And that means if I take the negative of it, I should get a current in the negative direction. Now, upward of the normal vector tells me by the right-hand rule that this here would be my positive direction around the loop, right? And so there's actually a minus sign in Faraday's law. What is the current induced if I bring the magnet closer? Well, I increase the flux, so I want an induced current that's pointing downward, right? Like a north here and the south above, right? Repelling. And so the current is actually moving in the negative direction around the loop, right? So you can write it with the minus sign and use the right-hand rule consistently, or you can just figure out the magnitude using the equation and then worry about the direction based on Lenz's law. I always like to have consistency checks. And so I like to figure it out with the right-hand rule and then confirm after I have found it, yeah, this agrees with what Lenz's law told me. And then I know I did it right 2 ways, right? But either way gives the same answer. So either right-hand rule consistently or Lenz's law consistently.
So for this one, is it negative or is it absolute value?
There are 2 ways to think about it. If you just worry about the magnitude, this equation is correct. But if we use this equation, we also have to use Lenz's law to figure out the polarity, right? Or you can write it in this way with the minus sign, and that gives you, together with the right-hand rule, then the orientation. So again, if I select somewhat arbitrarily the upward direction as the positive direction, then I select an orientation here for my arrows around the circumference of the enclosed area. And then that's going to be the current due to that EMF is in the opposite direction of that. Or in other words, if I just had this cut, I would not get a current, but I would get a voltage across this, right? Across this gap. And the voltage would be such that this would be the positive side and this would be the negative side, right? Sending the current that way around. So there's different ways of thinking about it, but they are complementary and should give you the same answer, right? There's the same physics going on, no matter which way you think about it. All right. Now, like I said, it's kind of arbitrary to call the upward direction the direction we assign the positive for this normal vector, right? How did I know upward was supposed to be the right choice? If I had chosen instead downward to be my normal vector, Then by the right-hand rule, now my thumb needs to point downward because I've chosen that as my normal direction. Then I get positive in the other direction, right? Positive is now clockwise around, right? And downward, well, with this convention, my flux is now negative, and also it's increasing because I get closer. It's it's downward, but it's still increasing, right? And so it's negative and increasing. So this here is negative. And then I have another minus sign that cancels that. And so for the current, I get the same direction. Does that make sense? So if I choose the n to point the opposite way, I get the sign of my flux changing. But I get the same direction of the current, right? All right. So if this way of figuring out the direction is confusing, we've just gone through Lenz's law, which is just as good a way to figure it out, right? Either way, you should get the same answer. All right. So we want to apply this, but we've been at it for a while. So let's take a little break for 5 minutes or so and then continue. All right. If you like, come and play. Can you feel it push? Yeah, right. So.
I actually have like none. So is it actually absolute zero resistance, or is it just so minuscule?
Well, you still get, eddy currents around the small circuits, so it's not only zero, but again, it's we now see that it's about the area that's enclosed, right? The flux. So those tiny loops don't have as much of an effect as the bigger loops. So it's pretty negligible. You can try this one where you have the bottom connected. You still have. So that one is a little bit more than the open prongs, but less than the other one. So.
The same thing is like what you demonstrate here as well happens. I've seen the dropping a magnet down a copper pipe. That's the same idea.
That's the same idea. Yes. Yeah, I didn't bring that one. So yeah, you can hold it and prevent it from dropping sideways, but then,
Oh, whoops.
So that's closed at the bottom, and so then by the other one for comparison.
I just watched Dylan joke last night. Yeah, it's not bad, man.
Right? If the small one doesn't fly as high as the large one, then let's put two of them on top of each other. Right? Why wouldn't we? So if you are joining online today and you are disappointed to miss all the fun in person, just talk to me after class one of these days, and I take you to the demo room and you can play around with it yourself too.
So do they have longer versions of the magnetic thing that also put more power through it so they can shoot stuff farther and faster?
There are, I'm sure, military applications, for example. I don't really know, but yeah, once we have the basic ideas, you can, how far do you want to shoot something? How much, power do you need transmitted? How do you have that available? How can you, once it slides off, you don't continue to accelerate it, so you would need a longer coil. But you can run some numbers on that and see if it's feasible. So yeah, and instead of shooting a ring, you can magnetically propel say a train, right? We talked about maglev trains where it's just levitation to reduce friction. But you can also use this to propel, right? Once your maglev train floats, the whole point is to not have friction, but without, wheels turning on a rail, how do you then get propulsion? It doesn't have a rocket at the end, right? So you still need somehow to pull it forward. And so, yeah, you can do that, of course, by having either induced fields in the train interacting with fields at the rails, or anyway, different ways you can think about it, right? So different applications. Well, all right, let's look at a little bit more on this. So we talked about Lenz's law and then Faraday's law to add numbers to it. Maybe it's worthwhile to again just briefly talk about the units. So induced EMF is minus the change of the magnetic flux with respect to time. And so we know the unit of 1 volt is equal to Weber divided by a second, right? Rate of change per second of magnetic flux. And flux was Tesla meter squared per second. And so, you know, however you remember the connection of these units, but 1 Tesla is volt second per square meter. We have written that down before when we defined the magnetic field, right? So the units work out, right? We also wrote down, for example, the magnetic force is Q V cross B, right? So let's look at that one with the units real quick. Newton is Coulomb times meters per second times Tesla. Let's check if that's true. Well, Coulomb per second is an ampere, right? So ampere meters times Tesla. And now a Newton meter is a joule, right? Newton times meter, that's work, mechanical work. That's a joule, or that's a watt for 1 second. And the watt of electric power is a volt times an amp for a second, right? Or a Coulomb times a volt, accelerating 1 Coulomb of charge to 1 volt of field gives me, takes an energy of 1 joule, right? And so I multiplied with meters, so I need to multiply with meters on the right side as well. And so then I can cancel my amps, and I again have Tesla as volt seconds per square meter as before, right? So however you want to, you know, do this, for some reason, I'll admit that I never quite remember what a Tesla is, if you ask me, and I need to actually look at some of the equations and figure out the units this way. But the point is I can figure it out, right? So either way, it needs to be consistent, right? So Tesla is a volt second per square meter. All right, so let's see if we can revisit what we've looked at early on. We've already looked at this setup and we explained what happens in terms of the motional EMF and so on, right? But we can also look at this now in terms of the flux through the area enclosed, right? Clearly, this loop encloses an area, and that area is growing if I pull this way, or shrinking if I push the other way. And so what's the change of flux over time? Well, it's the change of field times area. And what's changing here and what's constant? Well, the magnetic field is constant. How far the rails are apart, that's also constant. But the x, that's changing, and dx by dt, that's just the velocity, right? And so directly from Faraday's law, we are getting the same VLB that we saw on one of the slides early in today's lecture. So it's another way to say that, Faraday's law is consistent with the description we had before, right? I just wrote down Faraday's law without really justifying it. I didn't explain where it comes from, right? We talked about the general principle, and I showed that that happens in Lenz's law, but quantitatively, why does Faraday's law look the way it does? Well, mathematicians never accept proof by example, but this is at least a consistency check, right? If we apply Faraday's law to a situation where we already calculated the answer and we get that same known answer, then Faraday's law may not be proven, but it's at least plausible, right? We could be more rigorous at deriving Faraday's law, but maybe this satisfies our, desire to prove that this is the correct expression, right? At least it works in this particular situation. And so, we've looked at this setup in some detail before, and now in this framework of changing flux, and we are getting the same expression. So Faraday's law is in fact correct, right? All right, so for electromagnetic induction, we need to make some simplifying assumptions about wires and magnetic fields. In practice, we won't ever have a region of uniform field and then zero field next to it. It won't ever change so abruptly. But we can maybe assume that to solve a problem and get an approximate, close enough, good enough answer. So then draw a picture or a circuit diagram, use Lenz's law to determine the direction of the induced current and find the magnitude using Faraday's law. If we have an n-turn coil instead of a single turn, then of course we get n times the effect. That's why I could launch the ring with many, many turns of wire here, right? I think that's really pretty straightforward. And then the size of the induced current, if that S1 is given by Ohm's law. And then do all the usual consistency checks. All right. If I have the loop shown and a magnetic field pointing out of the page, that's changing according to the graph also shown, then what's the induced electromotive force around this loop, which is going to result in a current flowing based on the resistance of that loop. All right, so we really need to do this whole thing, right? Minus d by dt of the area times the magnetic field. And in this case, the orientation is such that I don't need to worry about the cosine theta, right? All right, what am I going to get with the numbers shown? half a Tesla in a hundredths of a second is 500 Tesla per second, right? Times 4 centimeters squared. 500 times 4 is 2000, times centi is 20, but centi squared 0.2, right? So, sorry, 0.02. So, all right, well, let's write it down correctly. Clearly, I just stumbled myself. 0.2 wasn't a choice. I know I was off by a factor of 10 if I had to mark a choice. So let's see here. We have an area that's constant, and it's 4 times 10 to the minus 4 meters squared, and we get a dB by dt, which is 0.5 Tesla per 0.01 seconds, or 5 Tesla in a tenth of a second, 50 Tesla per second. Oh, I think that was where I got my factor of 10 wrong, right? I think I said 500 instead of 50, right? Anyway, then you multiply these two things together. dVm by dt is dB times A by dt is 50 times 4 times 10 to the minus 4 Tesla square meters per second is 200 times 10 to the minus 4 Weber per second is 2 times 10 to the minus 2 Weber per second volts, right? 0.02 volts. All right. Okay, so if there is a wire, we know what the direction of the current is in that wire if the magnetic field changes. But what's driving the current is an electric field, right? And so even if there isn't a wire, there is still going to be an induced electric field, right? What's pushing the charged carriers is an electric field. And so the presence of the electric field doesn't rely on there being a current in a wire. Even without that, we still have the electric field at every point in space, right? It wouldn't make sense otherwise, right? The changing magnetic field isn't like taking pictures of its surroundings to figure out where there is a wire, right? It's just producing an electric field everywhere in space based on Faraday's law, right? And then a current would flow if there happens to be a wire that allows a current to flow, but the electric field is generated everywhere in space, right? So now maybe if you look at this, you will wonder, but where is the center point? Suppose I have a uniform electric field over a large area, and I just increase it. How do I know that, you know, this vector has to point this direction based on this being the center of all those circles, right? So there's maybe it's a little bit confusing after all, but but we know, okay, if the area is constant, then the change in flux is due to the change in field. And we said that's an electromotive force driving a current around the ring, and the electromotive force is electric field times distance, or in this case, the integral around the curve. And so this looks very different from what we had on the previous slide, but really it's just this side. This is, if there is a wire, this is the EMF in the wire, right? Force times potential times field times distance gives me the potential, right? So, all right, so we can write this down in this way. You can use some mathematical theorem to write it down in terms of, not a large integral around the curve, but write it down at a point in space, have a different form of Faraday's law that avoids this ambiguity where is the center of the circle. But that's another way of writing Faraday's law. Okay. It works for any closed curve. And if I were to draw another curve, then the Faraday's law would still hold true. Okay. All right. So what does an induced electric field do in a solenoid? Well, as the current through the solenoid creates an upward pointing magnetic field. As the current is increasing, B is increasing, so it must induce an electric field. Okay, what's the direction of that electric field? Well, if it's increasing upward, then to counter it, we get an induced clockwise field, so that if there were currents, it would provide a downward magnetic field. Well, that may not be necessarily happening, but you see this induced electric field is countering the direction of the electric field in the wire that's driving this current, right? So Lenz's law still applies. And so we look at this from a top view. We see that the integral of EdS is, well, taking E to be constant, 2 pi r for the circumference. That's going to be A times dV by dt. The area is pi r squared of that circle. And then we have the rate of change of the magnetic field. And so the strength of the induced electric field inside the solenoid is pi cancels, one factor of r cancels, and the 2 moves over r over 2 dB by dt. And so we have an electric field induced clockwise inside the solenoid. And so, all right, what's the magnetic field? If the magnetic field is decreasing, pointing out of the page as shown, what's the induced electric field? Decreasing out of the page. So if you can think about if there was a loop, then what would be the effect on the loop and how would that produce what electric field would produce that current direction. Right. So getting late. So it's the counterclockwise. So again, if it's pointing out, but it's decreasing in magnitudes and it changes into the page, then such a ring would need to produce a magnetic field out of the page to counter that. So I would have to have a counterclockwise current, which would be produced by a counterclockwise circulating electric field, right? Okay. All right. So then again, using our right-hand rule, we can then write Faraday's law with the minus sign and write the integral of E ds. The induced EMF is equal to minus d phi magnetic by dt. All right. Okay, so that's Faraday's law. Here we have axis for the magnetic field pointing into the page, and our red arrows always indicate the electric field, right? All right, that's an induced electric field. Now, what if we turn it around? So as we know, the changing magnetic field induces a circular electric field, but also symmetrically changing the electric field induces a circular magnetic field. Okay, so this induced magnetic field was first suggested by Maxwell, James Clerk Maxwell, in 1855, and that's what leads to electromagnetic waves then. Okay, so this, so changing magnetic fields induce an electric field. That's Faraday's law. And changing electric fields induce magnetic fields. And then if we put both of those together, we end up with electromagnetic waves. We'll discuss this in more detail, how this comes about. But an electromagnetic wave propagating, for example, in the plus x direction, is actually waving electric and magnetic fields that are perpendicular to one another and moving. Once we follow in more detail along what Maxwell did, we'll see that the speed of this electromagnetic wave is predicted to be 1 over the square root of epsilon naught times mu naught. Those two constants that came in to make the units work out, and the 1 over 4 pi epsilon naught, right? The dielectric constant and the permeability of free space. So permeability and permittivity of free space. And we of course know what these are from doing electricity and magnetism experiments, tabletop experiments, and we can substitute in the numbers and calculate what we would predict for the speed of our electromagnetic waves. And in 1885, the speed of light wasn't as well known as we know it today. but it had already been measured. And so Maxwell immediately realized that the electromagnetic waves he predicted were moving at the speed of light, and that light was an electromagnetic wave, but that the frequencies of the spectrum of visible light are only some of the possibilities, and there should also be electromagnetic waves that we can't detect with our eyes. There would be electromagnetic waves with any frequency. And so pretty soon after, Hertz and others observed radio waves and so on, observed circuits emitting waves that could get picked up a distance away by a different circuit, right? And so now we know the entire spectrum of frequencies all the way from very long wave, radio waves to FM radio at 100 megahertz and so on, all the way into infrared radiation and the spectrum of the rainbow from red to blue to UV, and then even shorter wavelengths, deep UV, and then X-rays and so on. And so electromagnetic waves are directly an outcome of this, and we'll look at it in more detail. There's also another application is generators. And so a device that transforms mechanical energy into electric energy. And so in a hydroelectric dam, you see those large generators, you see the shaft of the turbine that's spun by the water flowing through, and that mechanical kinetic energy of the water is turned into electric energy by electromagnetic induction. And the device that does it doesn't exactly look like the motor, but really pretty similar, right? So if I turn my coil, here shown with just one loop, but if I use n turns on my loop, I just get a factor n stronger output voltage, right? And it's just the induced voltage. In this case, I don't really want to have a change polarity because I can transmit an alternating voltage, or once it moves in a wire current, alternating current AC, right? And so as the orientation of my loop changes, I have my normal vector point either with the magnetic field or against it. And hence, as time advances, I change the sign here. So this is sometimes positive, sometimes negative, right? The current as shown here changes direction a moment later, right? So now we have an alternating current. And well, if we use the generator in this way, it's n turns, and Faraday's law, the area is constant, the magnetic field is constant in this case, but the dot product of those two, the flux also has that angle in it, and that changes at a uniform rate. And so we get just the d by dt of, well, really of the whole thing, but these are just constants that pull out of the derivative. And then the derivative of cosine is minus sine, and the inner derivative of omega t is just omega pulls out, right? And so we see an alternating current generator produces a sinusoidal output waveform, and the stronger the magnetic field, the stronger the EMF, right? No magnet, no induction. The larger an area I have, the more output I get. The more turns I have, the more output I get. And if I don't spin it at all, then of course omega is 0 and I get nothing. So if I spin it faster, I also get more, right? So the area I can make larger if I have a larger magnetic field available. So that has practical limitations. The strength of my permanent magnets is limited. I can maybe use generators with superconductors to produce the magnetic field, but then I use energy to keep my magnetic field up. Omega, I can always crank faster, right? But then the mechanical wear and tear also gets larger, right? And so in practice, 50 hertz or 60 hertz, depending on if you are in North America or in Europe, is the standard, right? One of those two frequencies. And we get an alternating current. So NBA, not March Madness, but NBA omega sine omega t. All right. And we can plug in numbers and figure this out. Once we have an alternating current, we want to transmit it. And in order to minimize transmission line losses, we really want to transmit it at as high a voltage as possible, right? Because what was our radiate? If I have a voltage and I have a cable with some R for my, for my wire, for my transmission, and then I have some load. Well, what's better if I have a high voltage or a low voltage? Let's say at the load, I want a low voltage, but maybe I can change the voltage as I get close to the load. Right, that transformer that's hanging on the utility pole at the end of your street. Okay, so let's consider just the transmission line losses. Okay, so I want power delivered is voltage times a current. But the power dissipated in the resistor, well, that depends on how much current is going through, right? In each case, I also get a small potential drop across the resistor, which is I, but hopefully that's reasonably small, right? But either way, to deliver power, I have to have a current going. And so the loss is RI squared, right? Because the voltage drop across the capacitor is RI. And well, the resistance, I can use, a larger cross-section cable for my transmission line. So I want to keep the resistance as small as possible. But we see I also really want to keep the current as small as possible. And how can I do that? Well, I want to deliver power, but I can do that either at a high voltage with a low current or at a low voltage with a high current. And to minimize transmission losses, clearly I want to transmit at a high voltage. Okay, so those very high utility poles that carry electricity from the Wolf Creek nuclear power plant all the way to Wichita. They can run at 100 kilovolts order of magnitude. There are, it could be 380 kilovolts or whatever, but I don't want to get into engineering of the power grid. I want to stay with the physics, okay? But we want to have high voltage on our transmission lines over long distances. But having 380 kilovolts in your outlet is probably not a good idea, right? We just saw these sparks that were not so dangerous, even though they were at that voltage. But you really don't want to have those sparks fly when you plug into a USB charger. And so for in the house, you want lower voltage. And so we need to have a way to change voltage. We need to have a transformer, transform from a high voltage to a low voltage at the different stages at the substation. Where's the next one? If you drive on Hillside past 9th Street, you look to the right, there's one of those substations, right? You've seen them, right? And then again, from there, it distributes into a neighborhood at, still significantly higher voltage than the 110 you want to get. And so then at utility poles in the neighborhood, there are those transformers mounted up there that then get it down to 110 volts into your home, right? Depending on where you live, some neighborhoods now have much of that underground, and you see those green painted utility boxes that have those transformers inside mounted on the ground, right? For reasons of cooling and so on, often those are filled with oil, and so then when you have lightning strike and you get high current, the thing explodes. Well, that's some of that oil can catch fire, right? I don't know if you've ever seen some of those things. Anyway, all right. So how does a transformer work? We have, say, from a generator, voltage that changes, and then I have a coil on the other side of my iron core, and then I have a load connected, and I have a different number of turns. Well, the EMF generated in this coil, induced by the magnetic flux going through, is N2 times whatever that changing flux is, right? But also on this side, well, as the current flows through here, it's producing a magnetic field in the coil. We've wrote down that equation before, right? For a given current, we know what the field is. And so that depends on the number of turns in my primary coil. And so the ratio of those numbers of turns is how V2 is either less or larger than V1, right? And so let me plug this in one more time. I can either shoot the ring into the air, or I can turn on a current in this coil and have something like an iron yoke trapping the magnetic field lines so they don't spread out, but they are kind of going through and then close. And so no effect, but as soon as I put it over here, I get a coil on the bottom here being the secondary and the load, just the light bulb. And so I have, wireless charging of your cell phone, right? We all have this at home nowadays. It's a pity. This used to be done impressive, and now it's like, yeah, I can charge my phone wirelessly at home. But anyway, all right. So that also works. Okay. So that's a transformer. All right, so we can transform up or down in voltage, and that's got plenty of applications, step up or step down, and so on. How does a metal detector work? Well, if I have a transmitter coil and a receiver coil on the other side, then it really requires the induced current will be constant if I don't mess with the magnetic field in the middle, right? But if I carry some metal through here where eddy currents are induced and that takes power out of the magnetic field, then I can detect that change in transmission between the transmitter and receiver coils. And I know that there's metal in between, right? So that's how a metal detector works. All right. Plenty of applications, but let's formalize this. I'm out of time, so I'm really going to talk about this next time. But the flux in a coil divided by the current, that's going to be the inductance of a coil, and that's the quantity that's kind of equivalent to capacitance of a capacitor. And so we'll continue next time how to calculate that for a solenoid and so on, and the unit of inductance. But with this, the next part of this chapter, we'll then get back to circuits and how to apply this in electric circuits. All right, so enough for tonight. Have a good evening. If you have time and interest, tomorrow at 2 o'clock, Professor Netta Enkelhardt from MIT is going to give the public lecture on the black hole information paradox. And so if that is at all interesting, look it up on the physics department website and join either in person in Hubbard Hall 211 to watch it there together at 2 o'clock tomorrow, or you can find the information to dial into the Zoom meeting on your own. All right. You too. Oh, I think my phone died anyway.
Are we anywhere close to finding what quantum gravity